done, then I'll get to the phone. So interrupts that have nothing to do with the program it's running, I handle them when convenient. I'm processing an instruction, the interrupt comes in the middle of the instruction. What do I do with it? I ignore it until the end of the instruction. Now I'm at a place where I have a nice consistent state. I can now go and deal with the interrupt. So I don't deal with the interrupt when it occurs, I deal with the interrupt when it's convenient. If I've got a pipeline machine, I've got lots of instructions that are in the middle of processing. Interrupt comes in, what do? I start bringing in instructions, allow the pipeline to drain. Now I've got a nice, clean, consistent state, and now I can deal with the interrupt. So I deal with the interrupt when it's convenient. When do I deal with the exception? I fetch an instruction, I discover it's an illegal opcode. Do I wait to the end of the processing of the instruction, or do I deal with it right there? Right there. I got a page fault. So I fetch an instruction, I decode it, I figure out the address, I go to memory, I discover it's not in memory. Do I finish, or do I deal with it right there? Deal with it right there. Normally, exceptions are dealt with when they're detected. So, why these two different things? It has to do with the cause. Context. So I've got two kinds of context. You know that. You've got system context and you've got process context. Since the interrupt is external to the program running, what context do I deal with the interrupt in? System context. Since the exception is part of the process running, what context do I deal with the exception in? The process context. Priority. So I'm running my process at a priority. Priority is a sense of urgency. I'm interrupting this process because something more urgent needs to be dealt with. So the priority of the interrupt is willing to interrupt the process it's running because it's more urgent. If it was the same level of urgency, it wouldn't interrupt them. So the priority of the interrupt is going to depend on what the priority of this event is. Somebody pulls the power out of the power cord, you're going to deal with that event. And then a machine check comes along. What do? Stop dealing with the power thing and start working on the machine check problem. Always working on the thing that has the highest priority. So the priority depends on the priority of the interrupt. How about exceptions? So I'm checking along, and all of a sudden I get a page fault. That is, the thing is not in memory. So I need to execute the page fault handler, that operating system routine that is going to go to the disk and grab what you need and put it in physical memory so you can actually access it. So what about the priority of that handler? Higher priority or lower priority than the process it's running? Who says higher? Who says lower? Who says something else? Anybody? Yeah.
The same.
Why the same?
Because there's a problem with the current process.
Yeah, so there's no change of urgency because it couldn't get the memory it needed to carry out the work. So exceptions say almost always the same priority. Maskable. Can I ignore? Can I ignore an interrupt? Most of the time, yes. So for example, you've dealt with keyboard interrupt. You could be running your program and you know about the interrupt enable bit, turn it off. Some yo-yo is banging away, wants to get at the machine from the keyboard, and you say, screw you, I'm too busy. Right? You can mask the keyboard interrupt. You can still have polling going on the program control, but the interrupt enable bit determines whether or not that keyboard actually interrupts or not. Most interrupts, since they're external events, can be masked. The two common ones that can't, machine check and power failure. So maskable interrupts, most, or almost all. How about exceptions? Gonna take a page fault. Nah, I don't want to deal with page faults today. I'm too busy. Makes no sense at all. So, maskable, practically none. I'll say few. Almost all exceptions, since they're caused by something internal to the running program, can't be masked. They need to be, they show up, there's a problem going on here with the program it's running, I need to deal with it. Okay, so that's my little assist to Professor Erez's lecture. Yes?
Can you define the context, like the process and the system? I'm not sure if you talked about that.
You haven't talked about, so you don't know what a context switch is yet.
It sounds familiar. Did you talk about that?
So the unit of processing, from the standpoint of the architecture, is an instruction, the atomic unit of processing. You process an instruction. You don't do half an instruction. You don't fetch the instruction, decode it, figure out the address, and then say, ah, screw it, I changed my mind. You know, you either do the whole instruction or none of it. And with a fault, which you almost always have, which you, not almost, which you, yeah, almost. What you almost always have to do is back up to the beginning, deal with the problem, and then move forward. At the operating system, the unit of processing is the process, not the instruction. And the process involves several things, some of which you used to already. Program counter, you know about that. That tells you where to find the next instruction. The process status register, PSR. And different machines have different names for it. Intel calls it a mask register. The VAX called it a processor status long word. Different machines have, ARM calls it a control register. It's bits that tell you about the priority you're running at, the level of privilege that you have, the condition codes, because when you stop something, you better hang on to those condition codes, so when you come back, you have the condition codes that you set by that process, rather than the condition codes that were set by the code that was running the service routine, right? So you've got, oh, and your registers. So you have register 1, I have register 1. Same register? No. When you're running, it's your register 1. When I'm running, it's my register 1. So if they want to kick you off the machine, bring me on the machine, what do they got to do? Save your register 1, load my register 1. All the state information associated with the process. So we're giving you several. Program counter, the PSR, stack pointer, general purpose registers, system registers. Yeah, I don't know whether he's talked about x86's my brain has done it. My brain does this now that I'm an old man and over the hill. I'm thinking of a word and I can't find the word. It's buried somewhere back there. Segment registers, I came up with it. So you got a code segment register and a stack segment register and data segment registers, and they're all specific to the process that's running. So the unit of processing, as far as the architecture is concerned, is an instruction. The unit of processing, as far as the operating system is concerned, is a process. And associated with that process running is all this state information, which is collectively referred to as the context of that process. So when I stop running this process and I start running that process, before I can do that, I have to save that context and then load that context. I have to save what you think is in register 1, so that when I come back to you, you'll have that value. And then I have to load what I think is in register 1 because I'm going to be running me. Okay? Does that answer your question? Not yet really, so go ahead, try again.
Okay, so I get that you have to save those things, and I think they talked about that in 306, but what's the difference between how an interrupt would do that versus how an exception would?
So if an interrupt is doing that, then I work within the context of the interrupt, the system context, with all the information that the system has, the context of the system.
So you don't switch context in that case?
You switch to the operating system's context in order to be able to then process that interrupt.
Okay.
And if you're dealing with a fault, an exception that is part of the process running, then you're operating within the process's context.
Okay.
Now the word context is just so if I say task state segment, have you heard that term before? No. So that's what Intel calls the context, is the TSS. But that doesn't help you because, you know, in fact, I may have, you still have your 306 book? Yeah. So Appendix B, what I put in Appendix B was x86 stuff. So we spent the whole semester dealing with LC3. How does Intel work with x86? I can't remember now whether I put the TSS in Appendix B or not. You may check it out.
Okay.
Or you can do what everybody does, you know, Google, and it has all the answers. The trouble is, if it's Wikipedia, it may not be the correct answer, but that's a whole other thing. Okay, we done? So I have one little side. Go ahead.
How does the priority of an exception?
I cannot hear you if you don't speak up. You got to remember, I'm old, decrepit.
How does the priority of the exception like come into play? Like,
I'm sorry?
how does the priority of an exception like affect?
It doesn't. What did I tell this guy? This guy gave me the right answer. It's the same. If I'm processing an instruction and a problem happens with that instruction, why should that affect the priority?
No, but then
It doesn't make, go ahead.
So how does why do we even think about that priority? So if an
Why don't we think about that priority? I don't understand the question.
I mean, if an interrupt comes of a higher priority, then we'll handle first the exception and then the interrupt, or
So you gotta speak distinctly. Are you Bengali?
what?
Are you a Bengali?
No.
No, because you're talking English like how many Bengalis I got in the room? I've insulted nobody. Good. You have to speak distinctly and loud enough for me to hear you.
So actually,
You have to have pity on my old age, see? Go ahead.
So what I'm not understanding is how does the priority of an exception matter? Like, what role does it play?
I'm still not getting you. How does what?
The priority, we said that the priority of an exception is same as that of the process. So when an interrupt of a higher priority comes, what will happen? So the,
I take the interrupt.
so the exception, what will happen to the exception?
I'm sorry?
So won't the exception be first then interrupt?
I'm sorry? No, you have to speak in complete sentences, okay?
That's what I'm saying.
So go ahead. So explain the situation and I will try to answer it as best as I can.
So you
The
are-
correct answer that I give you may be I don't know, but we'll try, okay? So go ahead.
Yeah. So say you are in a process A.
Yeah.
It has a priority X.
Right.
It has there's some page fault. So
Yeah,
page fault
good.
exception. Now at the same time, if there's an interrupt of a higher priority than X,
Right.
what will happen? So
What do you think will happen?
I think the exception should get first resolved because you complete the instruction and then handle the interrupt.
Bump, bump, bump. So you through with all this? What did my, here it is. Actually, I've got plenty of white space here. So I'm chugging along. Time is moving in this direction. And started an instruction, I finish the instruction, I get a page fault, right?
Yeah.
So what do I do when I get a page fault? I back up to the start of that instruction, right? Now I'm here. I want to deal with the page fault. I am running with what priority? The priority of the process. An interrupt. So I get a page fault, and let's say that, let's have the interrupt come in here. So here's my interrupt, here's my page fault, okay? Interrupt comes in, what do I do with it?
Wait till the
Nothing. Nothing is the correct answer. I'm gonna wait to hear, right? Because I'm handling my interrupts when it's convenient. So I'm gonna wait to hear. But here, an exception happens. So what do? I back up to here. Now what do? What I'd like to do is fetch the first instruction of the page fault service routine. Is that what I'm gonna do? Yes or no?
That's what I was thinking.
Well, so think some more.
I think interrupt should be handled.
I'm sorry?
Interrupt should be handled.
The interrupt should be handled. So you answer your own question. Good for you. That's right. So the interrupt comes in, I ignore it when convenient. I'll handle it here. But in the processing this instruction, an exception happens. I back up to here. Now I'm in a consistent state. Interrupt has a higher priority. I don't deal with the page fault, I deal with the interrupt. Okay? So we did get through it, right? Not as quickly as you wanted, but we got through it. Question? Yes, sir.
If interrupts are dealt with when it's
I cannot hear you if you don't speak up.
when an interrupt is if an interrupt is dealt with when it's convenient, what do you do when something like the power goes out or like when a wire shorts or something? Like, can you afford to like drain the pipeline? What do you do in that scenario?
So you deal with it at the end of the current instruction, right?
Something like a power failure type?
Yeah, even in a power failure. You a double E?
Yes.
How fast can you, so you know about capacitors, right? And so you're going along with a voltage like this, and now you want to go to 0 volts and drain the capacitor instantaneously, right? You able to do that?
No.
So how does it actually drain? Yeah, well, what do we call that?
Excellent.
We call it, that's right, it's an RC time constant, right? Yeah. So it drains like so. And as long as we're above, let's say, this point, everything's cool. So how much time is this? Measured in what? Yeah, it's time constant is when it gets to a certain point, but time constant is when the slope of this gets to 0. You learned that a long time ago, but you already passed that exam, so you were able to forget about that. As long as the voltage is above this point, I can still be processing. So what I'm looking at is the time between when I pull the plug and when I get to the point where it's a problem. And this time is measured in what kind of units of time?
Nanosecond.
Weeks?
No, nanosecond.
Nanoseconds? I think you need to go back to your 411 lab and do some experiments.
Micro or milli.
Well, probably milliseconds, maybe. Fractions of a second where the fraction is not small. How many instructions can I execute during that amount of, how long does it take to execute an instruction? Well, what's the units?
Nanosecond.
Nanoseconds, maybe even picoseconds today, but let's say nanoseconds, right?
Mm-hmm.
Yeah. So how many nanoseconds in a microsecond? Huh?
1,000.
1,000. So I can execute 1,000 instructions. How big is my service routine? See? So I can be processing for a while before the power drops to a point where it's problematic. Okay? Does that answer your question or not? It does, okay. Anything else? We're gonna get the virtual memory today. Professor Eres is gonna be mad at me. Go ahead.
So if there's an exception and then an interrupt, and it goes to handle the interrupt, when it gets back, does it retry and execute the instruction, or does it immediately go to the exception?
Good question. So what do you, how How do I get you to give me the answer?
I was thinking that in some cases it'd be better to try and re-execute the instructions,
So,
but that could waste time, and it's very unlikely that.
no, so the process of initiating the exception is to recognize as a problem, put the machine back in the consistent state, load PC with the starting address of the service routine. All that is an atomic unit of time. Now we're ready to start processing the exception, okay? But the interrupt is of a higher priority. So what do? I push on the stack the program counter of the exception handler, the exception service routine, right? Which means when I come back from the interrupt, what do I start doing? The exception, yeah. You see that?
Yeah.
Okay, good. Any other questions? Moving on. Okay, virtual memory. We did get there. 9:36 p.m., really? I thought I said I'd let you go by 5 o'clock, so I don't know what's going on here. So what is it, 2:36? Is that what says it's reset by 7 hours? Is that the problem?
7 hours and 3 minutes, 2:36. Sorry, 2:39.
It's right now, it's what time?
2:39.
2:39. Okay. So I gotta do is add 3 minutes to the minutes and subtract 7 hours from the hours. I'm not sure whether my pea brain can handle all of that. Okay, virtual memory. So your program, load register 1 with A. A is a virtual address. It's not a physical address. It's a virtual address. Why do we have virtual memory? Well, there's a couple of reasons. The main reason, so there's the first reason, the main reason, then because we have virtual memory, we can then have the second thing. And both are important. I would like each user to think that he or she has as much memory as he needs. But I can't afford to buy that much memory. So what I do is I take your virtual address space. Most machines today, your addresses are either 32 bits or 64 bits. Today we actually have the machines you're running. If you buy one of these latest Intel chips, it's a 64-bit address. That means you've got 2 to the 64 locations of memory. I don't think you can afford that much memory. 2 to the 64? That's a big number, right? 2 to the 10 is 1,000. So 2 to the 64 is 2 to the 10 raised to the 6.4. So it's 10 to the 3 times 6.4, which is 10 to the 9. That's a hell of a lot of physical memory. How are you going to afford that? So what we do is we let you think you have all that memory, but we take all that memory you think you have, and we run it through a memory slicer. You all know about bread slicers. You get a loaf of bread, you run it through a bread slicer, and depending on how you set the dial, you either have more slices of thinner slices, or you'll have fewer slices of thicker slices. Intel sets that slice to 4K, 4,000 locations. The VAX had 512 locations. I have a PhD student right now who's looking at making that slice 256,000 locations. The days of the 4K slice are over. We should be looking forward because we have so much more memory out there. And for every unit, every slice, I have to have information keeping track of that slice. Now that slice, supposing you've got all this memory, we run it through a slicer, is it important that all that memory be in physical memory at the same time? Probably not, because you're only executing instructions from certain slices and you're only using data from other slices. And why would you need 1,000,000 slices when you can get by with 10? And if you only need 10 slices, then why waste all that extra physical memory that's costing money? Especially if I have more than one process that's running at the same time. Not really at the same time. I'm running and then I stop running this process and then I start running that process after doing this context switch that we talked about. And keeping track of where these slices are is also part of your context, and we'll get to that hopefully before we part company today. Analogy time. So you all graduate, I decide to hire you for my company. And we're going to use this room as my office building. And where you're sitting is your workspace. And if I give you a workspace, I got to give you a pad of paper, I got to give you a pen, I got to give you a laptop, and I probably got to give you a telephone. So I buy a smartphone. I've got what? I got 100 people in here? Buy 100 smartphones? Can't afford it. I know what I'll do, I'll buy 5. Because most of the time you don't need the phone. So if I buy 5 phones, and I'll say to Stephen, the TA, I'll say, Stephen, here are the 5 phones. Now, I want you, Stephen, to look at all my workers working. And if one of you needs to make a phone call, what are you going to do? You'll reach for the phone, which isn't there. But that's okay, because in reaching for the phone, Stephen will see you reach for the phone. He'll run up and put the phone down so that by the time you get your hand there, the phone is there. And so I can get away with having 5 phones, and that's enough for everybody. Because at any one point in time, there's not more than 5 of you that are going to be using the phone. And then when you get through with the phone call and you put the phone down, then Stephen runs and grabs the phone, puts it back into his bag. Damn it. A 6th person wants to use the phone. That's okay. Most of the time when you're on the phone, you're busy thinking, you're not talking. Stephen's pretty sharp. You can tell when you're thinking and when you're talking. So when you're thinking, he grabs your phone and gives it to the 6th guy. And then when somebody else, he gives it to him. And everything is cool. And then a 7th guy, and then an 8th guy, and now Stephen's going crazy because there are too many demands on these 5 phones. Who's taking the operating system course? Anybody? Yeah. So what do I call this process where Stephen's going crazy satisfying all these needs? It's a very simple word.
Swap.
They never, what?
Swap.
No. Swap is when he gets through with the call and then I give the phone to somebody else. What I'm talking about now is I've got 10 people who need to use the phone. There's only 5 phones, and so Stephen is running crazy trying to satisfy these 10 people. Yeah?
Is it panic?
No. Nobody knows the word. Go ahead.
Oversubscription?
I'm sorry?
Oversubscription?
It is oversubscription, but there's a very common term that I hope your operating system professor covered. Nobody. Thrashing. You heard the term thrashing? You've never heard the term thrashing. Wow. Thrashing is when the operating system cannot satisfy the demands of all the processes that are running, requiring these slices of physical memory to do their job. And what happens is the system runs like a dog, and enough people get sick of it and just log out and say, screw it, and then the number goes down, and so then everything is fine. Or the system administrator does what?
Buys more phones.
Buys more phones. Or in the case of a computer system, does what? adds more memory. The way I get rid of thrashing, which you've never heard of before, tell you, I'm not going to ask you to name your operating system professor, but you go back to him and you say, why did you not teach us about thrashing? Important concept. Cured by increasing the amount of physical memory, because now there's more memory available. I told you that when you load register 1 with the contents of A is a virtual address, where A is actually stored, and I've got to translate that virtual address into an actual physical address. Because when I say load register 1 with A, I got to first know, well, where is A? In which slice? Because when I take a page fault, by the way, the slices have names. They're called pages. You got to write it on the board, because if you don't write it on the board, the kid doesn't take it down, and then he won't remember it for the exam. So the slice is called a page, and it sits in physical memory in a thing called a frame. And so, question, what's the difference in the size of the page and the size of the frame? Answer? What did I just tell you? The page sits in a frame. What's the difference between the size of the page and the size of the frame?
No difference.
No difference. Good. Okay? So I take my physical memory and I break it up into frames, and now I have each user, and it has a number of pages, and some of those pages are in frames and some of those pages are not in frames. And the process is running because you really don't need all that virtual memory at every instant of time. And so there's no point in having your entire virtual memory in physical memory. When you get a page fault, what you do is take one of the pages that's in a frame that you don't need anymore, kick it back to the disk, bring in a page that into the frame that you actually want to access. So when you say load register 1 with A is a virtual address. It may be in a page that's on the disk. It may be in a page that's in a frame. If it's in a page that's in a frame, we say that the data or the page is resident. And then I can make the access. If we say the page is not in a frame, but it's out at the desk, we say it's not resident. We stop what we're doing, back up to the beginning, call the service routine, which is part of the operating system's memory management handler. In fact, one of the things I like about virtual memory is it should really be taught in 2 courses. In the operating system course and in the architecture course. And then you guys can pull the thing together and then you really get it, right? Yeah. The architecture provides the structure and the operating system provides the code that actually carries out the work. So, load register 1 with A, I first have to ask the question, where is this page? Is it in physical memory or it isn't? So every page has associated with it a thing. We don't use the word thing. If I say it's a thing, then it has a property of thingness, and that's a little silly. So the thing is called a page table entry. So I have a page, and this thing is a descriptor associated with the page. Every page has its own descriptor, often referred to as a PTE, for page table entry. What's a page table? It's a collection of these page table entries. So if I have my virtual memory, and somewhere I guess I can get rid of all this. What the hell happened here? That's this? Terrific. Can't we buy stuff that works? I don't know how many of you have been in the conference rooms in this building. but the conference rooms in the building are missing something. Anybody have any idea what they're missing? Huh? No. You can bring in a marker, come on, put it in my pocket, right? A whiteboard, yeah. There are no whiteboards in the conference rooms. What kind of an architect designs an academic building and doesn't put whiteboards in the conference room? So I did a survey of about 15 professors. I said, what's the most important thing to put in a conference room? Every one of them gave me the right answer, whiteboard. Why are there no whiteboards in the conference rooms? Because the building wasn't architected by a professor. And they didn't bother to ask. Okay, so let me deal with my virtual address space. Oh, let me give you one more little tidbit with my cockamamie analogy about phones. So load register 1 with A. And you know the virtual address of A, because that's part of the instruction. Do you know what physical address, what physical location, physical memory A is occupying? Answer is no. If you look at your program, you've all written programs in assembly language? Well, you all took 3 of you actually are dealing with LC3B, so you're writing programs even now. LC3B, as we cover it here, doesn't have virtual memory. We say, okay, the whole memory is physical memory. The reality is, in fact, have you had the lab yet? Where no, you haven't, because it has to come after the lectures on virtual memory. But what you're going to do in a lab coming down the road is you're going to convert the LC3B to handle virtual memory. So the addresses you have in your instructions are going to be virtual addresses. And those virtual addresses are going to be stored in physical memory locations. Except you're not going to have 2 to the 16 addresses anymore in physical memory, because not all of your virtual memory is actually going to be resident at the same time. That's going to be your job in lab, what's it, lab 5, I think it is, if I remember correctly, to add the virtual memory property so that your 16-bit address has to be converted to a smaller address, because we don't have 2 to the 16 memory locations, we have something smaller than that. But when you write your program, you don't deal with the physical addresses, you deal only with the virtual addresses. Back to your cell phone. How many of you have a phone? Not everybody? Some of you do not have a phone in 2018? Do you know the virtual address of your phone? Yes? No? What is it? So give me the, what do we call it? Common name for your virtual address of your phone. Phone number, right. Supposing you get tired of your phone, you buy another phone. Different phone number, same phone number? Huh? Same phone number, good. Virtual address. Now, your phone has a serial number on it. What's the serial number of your phone? No idea. Same thing is true with virtual physical memory. Load R1 with A. You know the virtual address A. You have no idea where it's actually stored. Same thing with your phones. And Stephen has these 5 phones, and he keeps swapping them among those of you that need telephones, and that's fine. You all have your own phone numbers. But the actual serial number, is it possible in my scenario of you all working for me, that some of the time you're using one of those 5 phones and another time you're using another one of those 5 phones? And it still works, because it's the virtual phone number, virtual address. So my cockamamie analogy keeps on going until finally people get sick of it and leave. Okay, so here's my memory, my virtual address space. We're talking about the VAX now as one example. I don't know whether I'll get through it today. If I don't, Professor Erez will pick it up after the exam. And then he's also going to talk about the x86's virtual address space. The VAX had a 32-bit virtual address space. And the leading bit 0 meant that I was talking about the processes space, and the leading bit 1 meant I was talking about the system space. So in fact, the last quadrant here, leading bits 1, 1, was never used. Reserved for future use, which is always a good idea when you're designing something. So all these addresses start with 1, 0, and if it's a 32-bit address, then how many bits do I have left in the address? 30, that's right. And so this is how much memory? 1 gigabyte, right? 2 to the 30, 1 gig. You all know that. You can do that in your head, right? 2 to the 20 is what? Meg. 2 to the 10? Kilo, that's right. So 2 to the 30 is a gig. So 2 to the 32 is 4 gigabytes. 1 gigabyte's not used. This is the system, and this is the process, your process. Now, it turns out that the VAX actually had divided the user space into 2 halves. The stack that went this way and the code that went that way. But I'm going to ignore that for now and just talk about this is my process space. Now, this is one process. I've got another process. What about the system space of this process? It's the same. It's the space that's occupied by the operating system. System space. So this is my process space for user A, and this is my process space for user B, and this is my process space for user C, and I share system space among all of them. Now, I told you that I take the virtual memory that I think I have, and I run it through my memory slicer. It's not a bread slicer. I don't end up with slices of bread. I end up with pages. So I should put my pages up here. So here's a page, and 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 a page. Here's my physical memory. How do I partition my physical memory? Into what? Frames. How big is a frame? The same size as a page. System space. Say I've got 3, 3, 3. Is the whole operating system resident in physical memory? No. Why would I ever want to put the whole operating system in physical memory? I'm only using a piece of it at one time. So let's say my system space has, is made up of 3 pages. It's really made up of 1,000,000 pages, but we'll say 3. What do I put here? KLM, because the pages are the same. And what about here? KLM. And how about this process space? Well, let me call those pages 1, 2, 3, and 4. And let me call these pages alpha, beta, and gamma. And let me call these pages X and Y. If I look at physical memory, I don't have 4 and 3 and 2 and 3. Oh, go ahead.
Why is the system memory half the size of the process memory?
So, I wasn't the chief architect of that machine.
That's why.
Yeah. So the real reason, because Bill Strecker, who was the chief architect of that machine, decided that 1 gigabyte was enough virtual memory to contain the entire operating system. And he provided 2 gigabytes. And remember, I said the process is going this way and the user stack is going this way. How much user stack space do I need in running an application? Depends. Good. You got the right answer. Depends. Depends on what? What the application is. That's right. So Strecker decided that he wanted to allocate 1 gigabyte of virtual space to the user stack? How much physical memory is devoted to that user stack? Depends. The whole gigabyte?
Probably not.
Probably not. Good, he's coming up with the right, well, you're reading my mind. You're actually giving exactly the right answer, see? Yeah, how much space? As much as I need. Ever write a program that didn't have a stack? Of course, come on. You've never written a program that did not have a user stack.
I don't even know what that would be.
Hello World?
How about a program that adds a column of numbers together?
Well, it has a stack, right? It's just empty.
The system stack. And so I have a name for the set of pages that are resident. And it's called the working set. The working set. Why working set? Because it's the set of pages that are needed to make things work, to allow the process to continue processing. And then all of a sudden I get a page fault. It would not be great. By the way, how long does it take to satisfy a page fault? How many nanoseconds? Forget nanoseconds. If I get a page fault, what I got to do is go to the disk and bring in, and the disk runs at, what's the units for the speed that the disk is running at? Huh? I can't hear you.
Rotations per minute?
So, yeah, right, rotations per minute. I want to access the disk. Am I talking about nanoseconds? Am I talking about fortnights? What am I talking about? Milliseconds, right. Okay? Talking about milliseconds. If I want to execute an instruction, what am I talking about? Nanoseconds. How many milliseconds, how many nanoseconds in a millisecond? Huh? Yeah, so we have a fancy word for that, it's called million, right? Right? A million. I don't know how many you think in terms of 10 to the 6th. Most of us think in terms of million. A lot.
Yeah.
So when you take a page fault, it's going to take a lot of time compared to not taking a page fault. If you're continually taking page faults every access, you're really in trouble, right? So we don't take page faults all the time. We have a working set, which is a number of pages to allow us to continue working such that the frequency of the page faults is small. Right? If the page is in a frame, then we say that page is resident. Each one of these pages, now you know, see what they look like. Each one of these pages has a PTE, page table entry, associated with it. So in fact, I've got a collection of these PTEs, and this is the PTE for page 0. PTE for page 1. PTE for page 2. Why do I have a PTE for every page? Because in order to do my translation from my virtual address to my physical address, I have to access the PTE. And if I have a PTE for page 0, page 1, page 2, how do I get that access done? Well, I need a base address, which is the address of the starting address of this page table. It's called a page table. Page table. If I take my address, load register 1 with the contents of A. Here's my A. My A has 2 high bits. Let's say it's a address in user space that you're processing. What do I want these 2 bits to be? I'm executing an instruction, and I want to go to a memory location in this region. What do I want these 2 bits to be? 0. Let's say the page, in the case of the batch, the page is 512 bytes. So how many bits do I need to tell me which location on the page if I have 512 bytes on the page? 9. Good. Page offset. How many bits in the address did I say? 32. How many am I left with?
20.
That's not rocket science. How many?
21.
32 minus 2 is 30, minus 9 is 21. This gives me the page number. If in fact I had the entire process that I'm using, then I would need a page table. How big? Big enough to accommodate how many PTEs? Anybody? Nobody. Where is the disconnect? I've got a gigabyte of memory. Each address in memory has 32 bits. Addresses are part of a page. There are 21 bits to tell me the page number. My page table consists of a PTE for each page. How many PTEs do I need to accommodate a full gigabyte of process?
2 to the power 21?
Up high. Go ahead.
2 to the power 21?
Yeah, 2 to the 21. And it turns out for this machine, a PTE is 4 bytes. So the size of the page table, if in fact I use the whole gigabyte, would be 2 to the 23. 2 to the 21 times 4 bytes for each PTE gives me 2 to the 23, which is how big? What is 2 to the 23? 8 megabytes. Good. So a full page table would be 8 megabytes. Most processors don't need the whole 2 to the 23. Much smaller. Have you ever written a program that required less than a gigabyte of memory? Some of you have written a program that required less than 512 bytes of memory. How many pages of virtual memory do you need if your program will fit, program and data will fit in 512 bytes? How big is your page table then? 1 PTE, 4 bytes, right? So in fact, in addition to the base register of your page table, we also have a length register telling me how many PTEs that I actually have. So I need a base register, and I call this the process base register or the P0 base register. And how many are there? Well, I need a length. So I have a process length register. Because most processes don't require the whole gigabyte. I want to find the address of A. So I need the PTE associated with that address. Where is it? It's somewhere in the page table. How do I find it? Well, if my page table consists of the PTEs for page 0, page 1, page 2, what do I have to do to find the PTE for the address that I'm looking for? I need this PTE because that PTE is going to tell me where in physical memory my A is really located. Okay? So what do I need in order to find my PTE? Page number. Yeah, go ahead.
Should there be some way to indicate whether it's in physical memory?
I cannot hear you if you don't speak up.
Should there be some way to indicate whether the page is in physical memory or not?
But that's downstream. Nobody?
It's the base plus the page number multiplied by the size of the
Which is?
page table entry, which is 4 bytes.
4. Right. Good. You all get that? What he said was, take the base address and add it to the page number after I've multiplied that page number by 4. So take my page number, multiply it by 4, add it to the base register, and that will tell me where to find the PTE. Nice little piece of logic, and bingo, I've got the PTE. Now I look at the PTE and I have, so PTE page table entry, it's a descriptor. All over the machine we have descriptors. What's the time looking like? How do I make this tell me the time? Ah, good. 10:15, so I've kept you 3 minutes late. I'm going to keep you another 10 minutes late. If you have to leave, you leave, but I want to finish off at least enough of this to bring it to a decent conclusion. The PTE has to tell you whether or not the page is resident. The high bit, a valid bit. If the valid bit is 0, then the page is not in physical memory. I've got to stop what I'm doing, back up, call the operating system routine, which will go to the disk, grab that page, put it in a frame that's available, and then set the valid bit to 1, and now start processing. Supposing the valid bit is a 1, then here I've got what we call the PFN, which is a page frame number, which tells me what frame that page is in. So if I want to load register 1 with A is a virtual address. I don't know whether it's in memory or not, but I know the page number. So with the page number, I can find the PTE. And with the PTE, I can tell whether it's resident. And if it is resident, I can tell what frame in physical memory it's located. How big is a frame number? Depends on how big my physical memory is. Supposing I have a megabyte of physical memory. So physical memory is a megabyte, which is 20 bits. How many bits do I need for the offset? How many bits to tell me what byte within the frame? What do I put in a frame? A page. 9, right. Since one page goes in one frame, if the page consists of 512 bytes, then there are 512 bytes in the frame. And so what I got left is what? 20 minus 9, or I got 11 bits to tell me the frame number. That'd be a pretty small physical memory. But for illustration purposes, that's fine, because now my frame number is 11 bits. So what's the process? I want to load register 1 with A. I go to A, 00 tells me it's in the page table dealing with the process. These bits tell me which page. I take that page number, multiply it by 4 because my PTE is 4 bytes wide, add it to the base register of that page table. I have a different page table for the system space. I'm talking about the process space. And every process has its own page table, which is part of the context associated with that process. So if I was running this process, this page 0 is not the same as this page 0. This page 0 belongs to that process. This page 0 belongs to this process. They would be occupying different frames of physical memory. And I want to be able to swap between the two. Swapping between the two means just saving the base register of one page table and loading the base register of the other page table. Because the base register and the length register are part of the context of the process. Page frame number in this example is 11 bits. Why? Because I only have a megabyte of physical memory, and if I have a megabyte of physical memory, and if the frame size is 2 to the 9, there must be 2 to the 20 minus 9 frames of physical memory. If the page is resident, Frame number tells me where in physical memory that frame is. One more piece of data and then we'll call it a day. I said there are two things that the virtual memory provides. One is it allows everybody to think they have this much memory where you really only have in physical memory a small part of it. Process A has pages 1, 2, and 3. Process B has, I forget what I said, but a subset of alpha, beta, and gamma. Doesn't have the entire space. Only has a piece of it. Only has the working set of that process. The other thing that the virtual memory system provides is the concept of protection. So that nobody gets, even though there are many processes that are in memory at the same time, you don't get access to pages that you have no right to get access to. So the PTE has a field called the protection field. By the way, a very short digression. If I get a page fault and I go to the disk to bring in a page, where am I going to put it? In a frame. There's something in the frame. What am I going to do with it? Write it back to the disk. What if I haven't changed that page since I brought it in? That'd be a lot of wasted time writing it back to the disk. So I have a bit called the modify bit. First time I write to a page, I set the modify bit, which tells me if I ever need to kick this back to the disk, I need to actually write it back to the disk. If the modify bit is not set, then if I ever need to use that frame, I just throw away what was in that frame. Last item, protection. So what I want to be able to do is protect the pages so that I need the proper level of privilege to access the page. And in fact, in the VAX, there are 4 levels of privilege. Most operating systems have 2 levels of privilege, privilege and not privilege. LC3B, I decided to have 2 levels of privilege, privilege and not privilege. I got 4 levels of privilege called kernel, executive, supervisor, and user. So I need to know what level of privilege I have. Secondly, I need to know what kind of an access do I want to make. Do I want to read or do I want to write? And what I do is I protect the page such that I assign the right to read or write depending on what privilege level you have. So what I got is 2 bits coming out of here, 1 bit coming out of here, my protection field, and that gives me a single bit yes or no, whether I have the right to make the access. You need to start your class, David.
Yes.
Give me 1 more minute. The protection code of each page determines what level of privilege is required to make access. You can have no access. For example, David's salary, Professor Pann's salary information, I can't access. Well, I can because it's a state university. Supposing this is a private university, I wouldn't be able to access his salary. My salary, I can access. Read or write? Read. See, you're getting it. And of course, the dean has write access to my salary. Okay? Okay. Good luck on your exam on Wednesday, and Professor Arrows will pick it up at this point.